I lied to you again. I'm not going over the test at the end of the test. And again, I'm going to try to do it Monday. I'm not going to forget entirely, I don't think, but we do have some content that we want to cover today. Okay, so here. Oops, nope. Wrong order. We'll get to that order later. Is the definition of the radian. Yes, we're all roughly pretty good on the definition of the radian. Essentially, you take how far it is around the outside, divide by the number of radiuses, and that tells you how many radiuses fit around the outside of the circle. That also happens to correspond to the amount of radians and angle that fits around the outside part of the circle. What's that? If you go through a full circle, sure.
Yeah.
Right. If you go through, obviously, a part of that, that's why we were practicing that yesterday, so that you knew roughly how many there are. Now, this chapter has a lot of connections all the way back with the kinematics chapter. Okay? So we're going to try to draw some parallels, hopefully, for you, so that you don't have to reinvent the wheel for new difficult concepts. Okay? Meaning, we discussed those two things in kinematics. What are they? First one is wrong. That is position and displacement. And what's the other name for displacement? No. Change in position. Correct. Yeah, that is position and change in position, or position and displacement. And we're going to transition those over here to angular motion, like this. So if you had to just draw some nice parallels, you should be able to figure out what those things are pretty easily. Let's actually start with the bottom right one. What's the bottom right one? It'll be angular, or change in. Close, but we don't usually use units when talking about these things. Okay, let me help you out. This one is displacement. This one is angular displacement. Now, the great news for you with angular displacement is forever it's been shortened to a nickname. And that nickname is something that you have used a ridiculous amount of times in your career. Angular displacement is usually shortened to angle. That is angle. That is what you have always done. 30-degree angle, your angular displacement is 30 degrees. That's it. Okay? Now, of course, I'm going to want you to transition to radians and that, but blah, blah, blah. We'll get into that later. So, what would you guess then the top right one is? No, the bottom right one is angle. Top one's not. Here. Got you.
Degree.
Displacement?
Angular displacement.
Thank you. Position?
Angular.
There it is, angular position. Now, the great news with angular position, if you don't quite get that, I'm going to draw a picture in a second to kind of distinguish between the two. We don't usually worry about angular position. I want to show it to you so you can separate, so you can know why I get angry if you don't write your deltas on your thetas. And it's just this. This is what you were doing yesterday. Here is a top-down view of a person facing forward, okay? And you draw kind of like some line out in front of them. That spot would be angular position initial. So I'm going to move that a little bit here because I'm going to run out of space. So then you do what you did yesterday in a lab, and somebody tells you to turn 1 radian. So now you're facing this way, a little bit higher actually. A little bit less, but that would be your angular position final. And like you said a second ago, this is change in position, so this is just change in angular position. So the space between those two spots is angular displacement. I don't want you to think a ton of time on that. Ideally, I want you to understand the separation between those ideas. It is just real quickly this. Hey, this is position 1. This is position 4 over here. This is displacement. Why? Because I changed what my position is. How much did I change it? I changed it by positive 3. Yes? So, hey, this is position, let's go here. This is position 1 radian. This is position 4 radians. Okay? When I go from here to here, That was a change in angular position. How much? 3 radians. That same type of idea. How are we doing? Yes, no, questions, where are we at? Now, like I said, good news is this guy is what you're very used to, okay? You're very used to, you spend a lot of time using it yesterday. I'm not too worried about this, but I do want to kind of give you kind of a little bit of a peek behind the scenes as far as some of these things are concerned. We're not going to use angular position very much here, all right? But let's move on to something that we are going to use a good amount. Continuing with the conversation in kinematics, right after talking about displacement and time, we're not going to do time again, we talked about this. What is that? Velocity. And by definition, what is it? What's the equation? The ratio of how much change in position there is to how much change in time. So we've discussed position, we touched displacement, we've discussed velocity. The other two on the other side of things that we're heading into now are angular position, angular displacement. So if you had to guess what I'm going to fill in over there on the right side, it's angular velocity. Now, before I get into the symbol of that, let's go ahead and come up with the equation, because I think you could just easily draw some analogies here. If you had to guess, what is the equation for angular velocity? Angle over time. Or if you want to get fancy, angular displacement over time. The symbol used for that you can tell that we're using kind of Greek letters over here in this chapter. So we continue with Greek letters, and this is omega. I know it looks like a W. I'm going to get mad if you say W. It's omega. That being said, you probably shouldn't say any letter at all. Just like if I said, hey, what's this equation? You wouldn't say V equals triangle X over triangle T. You would just say the concepts. Velocity equals displacement over time. So what is this? Angular velocity equals angular displacement over time. What should the units of angular velocity be?
Radians per second.
So close, but not quite. Degree per second is a good way to think about it, right? It's actually not that wrong, but it's just not the units that we're going to use in here. So in other words, here we go. This is my angular velocity. Actually, no. Before I do that, what does it look like if I have a velocity? Tell me what to do to demonstrate. Just walk through space. Okay, that's an angular velocity. You want to have that picture in your head. So what does it look like if I have an angular velocity? There it is. I have an angular velocity right here. What is my angular velocity? Well, to start you off somewhat easily here, I'm going 1, 1,000, 1, 1,000, 1, 1,000. My angular velocity is roughly 90 degrees per second, except we're not using degrees, so
1.57 radians per second.
correct. Those are the units that you're going to be using over here for angular velocity. Real quickly in your group, name just like some situations where something's regularly rotating angular velocity that we might probably describe in here. Pick 3, discuss in your group.
Look at those things.
Wheels.
I can't say what
Ferris wheel.
Carousel.
I mean, you said wheels, and then you went into a specific wheel. I feel like you're going to come with that.
Death trap at parks that you
Yes, and I love that. The death trap at parks. Yes, 100%. We will do that demo in here.
Yeah. Woo!
Blender.
All right, what do you got? Few examples. You totally talked to your group, right? You didn't just sit there and stare at me while you were doing. All right, what do you got? Give me an example.
Lame.
Yes, technically that's right, as there are a lot of them. Okay, that's like saying, hey, what could we use to describe velocity? Objects. Thanks. I want to show you a finger right now, but we're at school, so I'll show you this one. All right. Pick a slightly more specific situation. Ferris wheel. Great choice. That's a wheel.
A windmill.
Sure.
A rotating door.
Okay.
A carousel.
Sure. Or I don't know if you've heard this or not before, but the wheels on the bus, they go round and round. Round and round.
Round and round.
Now, to the idea of the door, I want to bring that up because you do kind of get this idea as though it needs to be a complete circle, that type of thing. It absolutely doesn't. Okay, if I take this and spin it in the air, right? Spinning it in the air has an angular velocity. It is changing angle over time. So yeah, it is fair to say what could have an angular velocity? Literally any object could, but you guys were describing examples that we could come across. Now, hello? It is? I do. You're welcome. You have such and such in your room? Yes. Never mind, I'll figure it out. Cool. All right. Okay. So let's just give you some context of radians per second. We already did 90 degrees per second. What would that be in radians per second?
1.57.
1.57, correct. So let me share with you for a human how ridiculous, by the way, I will now demonstrate for you 6.28 radians per second. Here we go. Okay, there it is. 6.28 radians. You can see that if you are turning today and you are pulling off 6.28 radians per second, you're going to come off as a crazy person to your friends. Okay? I want to give you a little bit of context on some of these. Now, before I actually have you calculate one, let me share with you kind of an interesting thing about the right equation as opposed to the left. And that is, when we move through displacement, there's not like a usual displacement, right? It could be miles, it could be meters, it could be feet. There's not a set amount. But if you think carefully in your group right now, there is an angle that we regularly use all the time to describe an object moving. What angle is probably the most common that every human being uses to discuss quickly? We'll be right back in like 20 seconds. It hopefully shouldn't take long if you can see it. What angle is regularly used right here? Figure out. Discuss. Use your words. Look at each other and not me. I know it should be obvious. I'm checking to make sure it's obvious, although for some of you it's obvious. I don't think for some of you it is, so that's why we have these conversations. What is it? Disagree. If it's moving, we're probably not using zero, but you're similar. So close, but not quite.
180.
I disagree. I'm going to tell you this. If a thing goes in a circle, I think you know the time of a lot of things that go in a circle when they go through this particular angle. The Earth around itself, the Earth around the Sun, the Moon around it, the Moon around the Earth.
360.
The 360 degrees. Therefore,
Oh, I think you're moving in a straight
No.
line.
6.48 radians.
6.28.
6.28 radians,
Woo!
otherwise known as 2 pi. Meaning, if you look at this equation, you kind of need two variables in order to get the other one, right? Same thing here. Unless you consider the situation, as we regularly do, in which it goes through a full circle. Yes? Now, because of the commonality of this situation, physicists have actually named the time that goes with it and given it a slightly different variable. Not very different, but it is capital T. So if you get a capital T, it's a little bit of a weird situation because it's backwards of it. It's actually not a variable. It's a constant of the amount of time that it takes an object to go through a revolution. So going back to my examples, that by the way, that value, that time is called period. Okay? So if I said what's the period of something, that's a fancy way of saying how much time does it take to go through a full cycle. Okay? So what is the period of the Earth going around itself?
300 in 24 hours.
Yeah, you knew you were halfway through that. I appreciate that you stopped yourself. I'm going to give you credit because you stopped yourself. 24 hours. And of course, Keyser, what is the what's the period of the Earth going around the Sun?
365 days.
0.24, but I'll give it to you. All right. Now, what about the Moon going around the Earth?
12 hours.
No. 28 days. 28 days. See, I'm going less and less well known here. Period for the International Space Station to travel around the Earth.
12. 120.
Give me units, dummy.
12.
4.
120.
3 months. Yeah.
I know some of you, this is a guess. Does anybody know? It's 93 minutes. It's 93 minutes for the International Space Station to get all the way around the Earth, which is insane, but I'll prove it to you later on. So, let me ask you this question to do. Yes, go ahead, Michelle.
Oh, I just had another question. So when you're like solving for like, if you have like an
angle that's both in the x and the y, would you use the same, like the little.
I don't understand that sentence, so let's back up. What do you mean angle in the x and the y?
So like, like, it's like an angle, like, it's in the x and the y.
I don't understand it. They're all at the x and the y. If I do this and I go here, that's moved in both the x and the y.
Okay. Maybe I'm just confusing myself.
It's okay. All right, we'll get into this. But all right, so do this real quickly in your group then. I'm going to ask you to use this to see your understanding. I want you to find the angular velocity of the second hand on the clock.
The z axis.
Sure. Okay, so that's an excellent question. We're not going to focus too much on it right now. We will have to focus on it. What it comes down to is by what axis are you on? Okay, so meaning if I want to, if we call this will be the x and this will be the y for my example. Okay, technically when something spins like this, its axis is the third unit direction, meaning it's technically spinning on the z axis, and so you just measure from this perspective, right? If it were measuring like this is actually on the z and the x, and your axis is here. But it's the same type of thing, right? How much angle does it go through in a particular amount of time?
Okay.
All right, discuss in your group. Do the calculation, not just on your calculator. Like actually write down the word. I know.
I did.
Oh, you did. Good. But I'm looking at a lot of people. I'm not saying just you. Okay. A lot of people around the room just grabbed calculators or literally were staring off into space.
Where do we have the
By the way, Isaiah, what you got there?
I got it.
They're brownies with Oreos.
No, I mean like I got
I don't need it.
Sorry.
I want it, but I don't need it. All right.
I got it.
Yes.
Dang it.
Discuss with your group. Your group should be figuring it out.
I don't understand the question.
Oh my god.
The second hand on the clock. So I am not, this has happened before, not referring to the first, second, and third hand on the clock. When I say the second hand on the clock, I'm talking about which one?
The second one. The actual second.
The one that ticks every second.
What is it?
The minute hand on the clock is the one that ticks every minute. The hour hand on the, you get the idea.
What is the question
Yes.
though?
The question is, what's the angular velocity of the second hand on the clock?
Okay. Well, okay.
Well, sure, that's the point of this.
So 60 seconds.
You don't need to know where the clock is.
You don't need to look at the clock at all because you already know the numbers that you need. Based on that last equation, what I'm saying here's the difference between these two. That could be any angle whatsoever. You might know that number, you might not. Okay? If you have only 45-degree angle, this is the one you have to use. This is the one you use when it goes through a full circle. So all you need to know is how much time it takes to go in a full circle. So let's humor ourselves here. Make sure we're on the same page. What is the period of the second hand on the clock?
60 seconds.
You're answering the next question. 60 seconds is what I was looking for. The question on the table is, what is the angular velocity now?
105 radians per second.
Yes, correct. In other words, you would say 2 pi divided by 60 seconds, and you should calculate 0.105 radians per second.
Would you be allowed to use, like, let's say you're doing a year, like, radians per year?
Technically, yes, although it's kind of like there's a standardized unit so that we can try to understand it a little bit better. Like if I told you how many inches something went in a year, you're probably going to go, well, that might be accurate, but it's unhelpful. I have no idea what inches per year is relative to anything, right? So what you usually do with conversions is you put it in terms of numbers that you already understand. So you would probably convert inches per year to either miles per hour or meters per second so that you could understand it a little bit better, right? It's like what I gave you the example yesterday. If I said 2,000 degrees, what is that? You're like, I don't know, but let me put it in context of something I already know. So you divide by 360 to get this blah, 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 right? So technically not wrong in any particular way, but on a test, I'm going to assume that you're going to go to a standardized radians per second so that you can compare it to stuff that we already know. All right, so what does 0.105 radians per second mean?
Every second it goes 1 radian.
Okay, or to put it into context, if you understand, remember that yesterday 1 radian is roughly 57.3 degrees, right? Okay, or roughly 60. So 0.1 radian would be 5.7 degrees, or rounding up, actually, the because of the 0.28, it'd probably be about 6 degrees a second. And if you think carefully, that makes really good sense that the second hand of the clock should go around 6 degrees a second. Why should that make really good sense?
Circle.
Because it should take 60 seconds, and there are 66 degrees in 360 degrees. So of course it should. Now, I've given you context, hopefully now, of 0.105. That's pretty slow, right? This is 0.105 is me spinning and taking how long to get around? 60 seconds. Correct. I told you 6.28 on the other end of the spectrum. You saw the ridiculousness of that. Let's do this one more time with another number, another unit that's regularly used in angular velocity, and that is, you're driving in a car. What measurement of angular velocity is regularly being used that you can see? Revolutions per minute. Correct. RPM are revolutions per minute. Does anybody know roughly what idle is on those vehicles?
1,000.
1,000, correct, because you see the 1, but it says underneath it times 1,000. Now, I still argue that 1,000 revolutions per minute is a dumb set of units for me to try to understand. Why is it a dumb set of units for me to try to understand? Because I can't even see a revolution. I guess I'll take your word that that's 1,000 revolutions per minute. So, let's do this. Take that 1,000 revolutions per minute and put it in terms of radians per second.
What does the revolution like mean? Is it like the wheel going around?
We're going to use a lot of words that mean the same thing here, and you've actually already used the word revolution relative to other ones. What does revolution mean?
It like going around the full circle.
Full circle.
So it's just the wheel going around?
Mhm.
Okay.
So that says when the car is in idle, it revolves all the way around, goes through a complete cycle 1,000 times every minute. What I'm asking you to do is calculate what that is in radians per second now. This is just a conversion. So just do the conversion that you know. Yes, sir.
Can you go over how to find like your tangent velocity?
You were
Okay.
skipping
Revolution is
3 steps
360.
ahead, buddy. I got a plan over here. I don't just wing this. If you'd like to see my plan, here. I think it's important that you guys know that I don't just like make this up on the spot, and that actually there has been a good amount of planning that goes into actually everything that I'm going to discuss with you. Okay? So what you just asked is over here.
What are we on right now?
Over here.
I don't understand.
So it's just a conversion. So you need to. What don't you understand?
I just like a revolution. I'm thinking is 360 degrees, but then I don't understand what degree you want to change it to now.
Well, I asked you what it was in radians per second. So
Okay.
another way to say that is you need to convert revolutions to radians. A revolution is
Times 6.2. Just gotta just gonna let her sit there and think about life.
Here we go. 1 revolution, how many radians? 2 pi, or 6.28 when you punch it in your calculator. Cool. Right now we are at what?
6280 radians.
Not the number, I'm sorry. What units would we be at right now if we stopped?
Radians a minute.
Radians per minute. So,
You divide by 6.
minutes goes on top, so it cancels. 60 seconds goes on bottom. You should get roughly 105 radians per second. Now, that being said, I still argue that radians per second, radians by themselves, especially at 105, don't bring me a lot of context the same way as 2,000 degrees yesterday doesn't bring me a lot of context even if I'm comfortable with degrees. So what I probably should have done to kind of give you a better idea is not done this step right here. Okay? If I don't do that step right there, what does that tell us?
How many revolutions?
So what is that?
17.
About 17, correct. So what it says is your engine at idle will spin 1,000 times per minute. That's not super helpful. It spins 17 times a second. Very, very quickly. Obviously, I don't think Spainhour pulling off the 6.28 radians per second is going to come anywhere near to that. As a matter of fact, your human beings, what probably are your human beings that would be the best at angular velocity? Correct. Your ice skaters that are pulling off currently quads and quints in the air in a very, very small amount of time. And you can calculate their angular velocity because if it's a quad, by the way, in case you didn't know this, it's technically, I think it's 4.5, 3.5. I think it's 3.5 technically turns. rod, so you could convert that to angular velocity and just figure out how long in the air, roughly 0.33 seconds, and you could calculate radians per second from that, but let's not worry about it right now. So that's angular velocity. I think you roughly got it, so let's go back over here and talk about a homework problem that I'm pretty sure that you're actually okay with. Oh no, I want to do one other thing. All right, 0.105 radians per second. That's second hand of the clock. I asked what it meant earlier, and correctly you said that's 0.105 radians every second. Sure, but also based on the definition of the radian, that means it's 0.105 radiuses every second. Yes? Let's say I turn around in 4 seconds. Okay? I go all the way around in 4 seconds. What's my angular velocity? Calculate it if you need. 1.57. Or this is the situation we talked about earlier, that roughly 90 degrees a second. Okay? Let me ask you a question. If I rotate around like this, okay, are all parts of my body going the same angular velocity? Yes. Why? Sure. I'm sorry. Explain that though. Why? How can you confirm? Yes, absolutely. All parts. My fingertips and my elbow are definitely going to the same amount of angular velocity because they're going. Sure. It's not quite well, but all I needed you to say is what I'm looking for is both of them are gonna go to the same amount of angle in the same amount of time. Yes. Like when my elbow goes 90 degrees, my fingertips go 90 degrees. Cool with that? Correct. Good. So next question for your group. Are all parts of my body going the same speed?
No.
Discuss why in your group real quick.
They're all radii. My child is saying
Oh my gosh.
Okay. So what's the answer? Why are they all at different speeds?
They all have different length radiuses.
I wouldn't say that. I mean, you're not wrong, but that's not the place to start to really understand. What's that? What does it mean to have a higher speed?
They go more distance.
I'm gonna say that. I would say differently than distance. They cover more space, more stuff, right? More feet, whatever. So why do my fingertips cover more space than my elbows? They make a bigger circle is pretty much what you need to see. Okay, this is a top-down view of me. Now, to the credit of Kieser, kind of stepping one step ahead of us here. To talk about the bigger circle that they make, we can simply see that they make a bigger circle corresponding with the larger radius, right? So, if I knew that Spainhour is spinning 1.57 radians per second, that's 1.57 radiuses every second. What's the only thing you need then to tell me how fast my elbow is going versus my fingertips? Size of the radius. Because if I multiply by the size of the radius in meters, I'm going to end up with meters per second. Yes? So 1.57 radians. If I know that my fingertips over here, just making up simple numbers, is 1 meter, then I should go with 1.57 meters per second. Whereas my elbow, on the other hand, say is a half a meter, should go through roughly 0.72 meters per second. So they're all going different speeds, even if they're going the same velocity. And I'm sure you've been using this equation, and I'll get to your question right after that, and it is this. The velocity that you're going, t, I know Kieser asked, but I'm going to ignore it again. I'll come back to it, is equal to the angular velocity times radius. Now you have 3 new equations right now. 1, 2, and all that's wrapped up together, I would argue. And this guy, 3. Now let me show you something very carefully about this guy. I like that this is a good definition of the radian. This is how I would put it if I wanted to talk about the radian, but I don't like it for the clean nature of it. So here's what I'm just going to multiply r on both sides, and this is what I'm going to get. The arc length that you go through, the linear value, is equal to the angular value times radius. And if you compare that to the last equation I just said, the linear value is equal to the angular value divided by radius. And here's why that makes sense. If I take that first equation and I divide both sides by delta t, what is delta s over delta t? Velocity. And what is angle divided by t? Angular velocity. Technically, these are the same equation. Now, on your homework, here's what I'm guessing you did on potentially number 9, if you're there, and you don't have to be, but there's a few other problems that do this as well. There's a discus guy that was going to throw a discus, and you're trying to figure out how fast the discus is going. So what you did is actually I'm going to take one step away from that conversation and point this out. This guy, by the way, even though it looks different, should be very, very familiar. And to show you that, let me show you real quickly. What angle is a full circle? 2 pi. And what do you call the arc length when it goes in a full circle? Is that familiar?
Yeah.
So the only difference between that equation and the one above it, maybe, one more, come on, is the one above it allows for any possible angle whatsoever. Circumference is just the very specific arc length that goes with that title. So with the person that did the discus, my guess is what you did is you took the 0.71 meters and you used basically maybe this equation, maybe just use circumference, they're the same thing. And with that, you found out how far it goes all the way around. You found delta S. And then my guess is to find the speed, what you did is you just took delta S and divided by delta T, standard equation that you're very used to. Yes? What I want to point out is that equation can be, that process can be done a second way. And the second way that you could have is this. You know that the discus guy goes around, you use radius first and then time. What if I use time first? Well, I know the guy goes around in a full circle. So if I use how much time it takes him to get around, that would give me his angular velocity. So in the first case, we used radius to get distance and time to get velocity. Here, we use time to get angular velocity, and then if I wanted to know the velocity, we would just use radius to calculate that exact same answer. But really, that's 4 different equations, but it's just doing it the opposite. Here we use radius first and then time. Here we use time first and then radius. Ends up pretty much the exact same way. Questions, concerns? Yes?
Okay, so when you said that it all depended on the radius for the speed, right?
Yes.
So when you're measuring your radius, so since you're connected, you would always measure from like the part that you're looking, the speed that you're looking at the part, all the way to the middle of the object.
Exactly. So like if you wanted to look at a person, right, you go, I made up some numbers earlier, you would simply measure from here to the elbow, from here to the fingertips. Technically, there's a whole bunch of different speeds on my arm. We would just be focusing on those. You could figure out what the speed is of my shoulder when I spin around, and obviously it should be slower. What should the speed be of the center of my body? 0. How come?
Because there's no radius.
What's that? Sure, but I think there's a better way to say it.
Well, it's 0.
It's not going to go anywhere, right? It's going to stay in the exact same spot. It's not covering any distance over time, so it shouldn't be moving. Yes?
If it's like an egg shape where the center of mass like isn't exactly in the middle, do you do it by like?
So the center of mass not being in the middle doesn't matter, but yeah, we're not going to deal with anything that complicated, but your radius would be measured from the center of mass, not the center of volume. Okay, moving on. Okay, so this chapter, the radians are just the heart of it, the very beginning. That's the tool. But we are now going to use that to transition into kind of the heart, the difficult part. I spent a good amount of time on radians and angle here because I really want you guys to hopefully have that fairly well understood so that when we get into the more difficult meat of this, you can kind of make that separation between this is difficult not because of radians, but because of whatever. Okay? So there's 2 sections to this chapter that are kind of hard to distinguish. So I'm going to do a demonstration for you to help you distinguish between the 2 of those. those, okay? The two sections of this chapter are this: change in direction versus change in orientation. Now, the reason why this is going to be difficult for you to see is that when we walk, as I'm about to show you in a second, we do both, okay? If I walk around the corner like this, yeah, that's a pretty standard way to walk, yes? How much did my angle change? 1.57 radians, correct. Now, I'm going to do that same thing again with only focusing on changing one of them. So the first part of this chapter is just changing direction, but not worrying about orientation. So here is changing direction and not orientation. What changed then?
The way you're moving. Your direction.
More specifically.
The angle you
Think
were
about that.
facing.
No, the angle I was facing stayed the same. My orientation stayed the same. What changed?
Direction of velocity.
So yes, you're right there. You're right there. But what do we use to say the direction we're moving? We've got 5 vectors now: displacement, velocity, acceleration, force, and momentum. Which one do we use to distinguish the way you are moving that you're describing? Like if I said I'm going this way, I'm describing an arrow. Okay, what arrow am I describing? Velocity. Correct. So you look here, my velocity is this way, and now my velocity is that way. Okay, that is changing direction of velocity without changing orientation. As opposed to, and by the way, how much did my velocity change? Angle-wise?
Or 1.57.
1.57 radians. Now, I'm going to do the same thing again. I'm going to move, but I'm going to change orientation and not direction. Okay, see the difference? Did my velocity change direction? No. Did my orientation, my angle change direction? Yes. They usually go hand in hand, but not necessarily always, so you have to distinguish between the two. So the good news is we're going to focus on the first one, which is what you're a little bit more used to. I mean, up until this point, if I told you that a car was going to the right, do we actually care whether or not it's facing to the right? Mathematically? No, we haven't worried about orientation yet, and we're not going to in the first section. Now, we mentioned a second ago that velocity is a vector. What makes it a vector? What's that? It has magnitude and direction. What is its scalar counterpart? Speed. And we would say that speed is just magnitude, right? So another way to say the vector is that it's magnitude plus direction. Since magnitude is speed, we could just say that basically velocity is speed plus direction. Is that fair? Okay, what's acceleration? The change in velocity over change in time. First thing I want you to see is I want to focus in on this guy real quick. So if a person is running to the right with a velocity and they see someone behind them that scares them, so they speed up. This would be velocity initial, this would be final. What is the change in velocity, or what direction is the change in velocity? To the right. We would describe it like this, almost like a third vector. Okay? It's very important for your sake that you kind of see these situations in terms of change in velocity and not just the initial ones. Or let's borrow an example of a problem that we did on the test. Okay? A person is diving into water. Their initial velocity is down, and what's probably going to happen to their velocity when they hit the wall? It's going to stop. Let's just say slow down, because you're right, they're going to stop. Let's just focus only a little bit after, so they're going to slow down. What is the direction of change in velocity? Up. Now, what you will notice in both of these two particular examples is that in the first one, velocity was this way, and because the change in velocity, acceleration was that way. And which of these two did it change? Speed. On the other hand, the second example, velocity is here. Oop, I think that's the wrong one. Acceleration is here. And which of the two of them did it change? Speed. we really haven't changed direction very much. So let's look at what direction change in velocity or acceleration would be if we did change direction. I'm going to give you a situation to look at, and you're going to try to figure out in your group that question. What direction is acceleration in the example Spainhour gave us? So imagine that you are, I'm going to try to paint a picture of something that probably happened when you were younger. I can't guarantee it happened, but very likely. You're on the playground playing tag, okay? You are not injured, you are being chased very closely by the person behind you playing tag. So you're running, and right here on the playground there's a pole sticking out of the ground, a solid pole, okay? And you want to change direction. What do you do? Grab the pole, okay? Let me get your money. I'll be right back. Thank you, Sebastian. All right, so here you go. You're running, you hit the pole, you grab the pole. What happens to you? Now, note real quick some important values that we've discovered. Your velocity is which way currently? Right now, velocity is this way. So I grab right here. Grabbing will apply force, specifically tension. Okay, now what's going to happen to you is you're now going to swing around. So what happens to your velocity? Changes. Okay, go. Now, you no longer want to change direction. What do? Let go. And once there's no more force, there's no more acceleration, so you continue forward. The example for your group, again, is in what direction was acceleration in that example? Discuss.
It's the confidence in the gap. I'm like, this wasn't speeding up forward, speeding up forward.
All right, so I've attempted to draw a rough picture of the top-down view of this person. Top-down is going to help you a lot in this particular chapter to see the circle. So, here's the person. In what direction is their acceleration in this case? Yes.
Towards the pole.
Towards the pole. Or, probably a better way to look at it, perpendicular to velocity. Now, as that happens, what's going to happen to, of course, the direction is it's going to change. So I drew it over here, but let me draw it a little bit of the way through. Now, the velocity is this way. Now, notice carefully in the middle of this, what am I roughly attempting to do with all sizes of these arrows? Why? No. Didn't say quite right. Speed is not changing. Is your velocity changing? Yes. Going back to the example up here, where these two examples changed this and didn't worry about that, the example we're looking at right now changes direction, but not the speed of the person. You can accelerate and not change your speed. Don't believe me? Try to get off the interstate going too fast. All right. Try to stay at the exact same speed. Yeah, don't actually. Okay, this is 100% facetious, but that's why I have to say this on the off chance. Okay, but yeah, imagine you try to get off one of those off ramps, big circular off ramps going 80 miles an hour. I'm sure you don't go 80 on the interstate, but let's pretend you did. Okay, I don't think it's going to go well. All right, now as you change velocity, what happens to change with the orientation of your arm? It also changes, right? By how much? Actually, it's about the same amount of angle. So what is the direction of acceleration compared? It stays at 90 degrees. And when you no longer want to accelerate, what do? You get rid of the acceleration, because if there's no acceleration, there will be no change in velocity, either speed or direction. How are we doing? Yes.
Why don't you speed up when you're, because the acceleration would, like technically your velocity is all in the y in that first picture. And you're accelerating to the right, so you're adding velocity to the x.
I am adding velocity. My change in velocity is this way. Now, one hard thing to see in this picture is it's impossible for me to draw an infinitely small delta v. This is a very calculus example that I'm asking you to kind of think of, because technically you're sort of right. Like, well, if I get going that way, won't I speed up that way? But I want to technically draw this infinitely small, because the very moment my velocity, my acceleration is this way, I change direction. And in that exact same moment, my acceleration also changes direction. Basically, if you look at it, it looks like this the entire time. It stays at 90 degrees. To counter that, you've dealt with an example that this wasn't the case for. If I throw an object off of a side, we know it's not going to go in a circle, it's going to go in a parabola. Why is this different? Well, this is different because I put a velocity this way, and what's the direction of acceleration here? Down. But the major difference between the example I just shared with you and this one is this one, acceleration stays pointing down. Okay? In the situations I'm describing, they stay perpendicular. Why? It depends on the context. Let's give you some context, okay? Imagine here you have the Earth, and we have a satellite going around the Earth. Now, the way that NASA puts these up is they simply put a velocity in the right direction, and then they can leave it. Why? What's going to provide acceleration to that satellite so that it doesn't go straight? Gravity. Okay, so you got gravity here that is pointing towards the center. The Earth, you'll notice it's nicely at 90 degrees. What I'm telling you is that when it stays at 90 degrees, it changes direction. If it changes direction consistently, what shape will it make? A circle. So here, it changes direction to go this way. Okay, and what does gravity in this case nicely do? Well, yeah, it also changes direction so that it stays 90 degrees to that right here. Or here's probably an easier example. It's going in a circle, right? Which way is the thing going right over here? Up. So if I let go over here, it's not going to go left. If I do a good job, it should go straight up. Which way should it go if it's on top? That way, or tangent. I got there, I promise. Okay, now you'll notice when it's going that way, which way is acceleration? Down. And it swings around, swings around, swings around. But as it swings around, both are changing. The velocity is changing direction to stay tangent, and the string is changing direction to stay at 90 degrees. So basically here it is. We're describing what's known as acceleration centripetal. Acceleration centripetal is not a new acceleration. It's the same definition as it always was. It's just that rather than the change in velocity going parallel, which would change speed, change in velocity goes perpendicular. Look, it's changing velocity over time. But instead of changing that speed, it's now going to change simply its direction. Questions on that? This is not an easy subject to get. And like I said, a lot of people struggle through this. Make sure that you're working on radians. Now, to kind of put a bow on tangent velocity, as well as add the equation in case you want to get going on this. And the quick thing I'll say about the equation, it doesn't make sense. It doesn't make sense. I'll go over it on Monday in further depth so that it makes better sense. It still won't make sense. Okay? I'll give you a lab. Luckily, we've already gone through a particular process in which if Spainor gives you an equation that doesn't make sense, you can go out to the lab and check and see whether that's true. All right, real quick, two things. One, what the heck do I mean by tangent velocity? Well, these are velocities because they have both speed and direction. But what have we already said about the speed of this guy here? It's not changing. So is velocity tangent to speed? Sort of, because it is an exact number. But it also has direction. But that direction is constantly changing. So rather than say this one's at 90, let me finish real quick. This one's at 90 and this one's say at 135. Instead of saying that, we just say it's tangent. Meaning, if you draw a radius, tangent means the line just keeps going at that particular spot. And here's the equation, if you don't already have it. AC equals tangential velocity squared over radius. Have a good weekend.